Today, we are going to solve the problem 2.7 of Griffith 4th edition, Introduction to Electrodynamics. The problem 2.7 is find the electric field a distance z from the center of a spherical surface of radius r, as shown in this figure. Uh, that carries a uniform charge density sigma. Remember that this is a surface charge density sigma, charge per unit area. So treat the case Z is less than capital R, that is inside this sphere, and as well as Z is greater than R, that means outside the sphere. Express your answer in terms of total charge Q on the sphere. Hint is given. Use the law of cosine to write R in terms of capital R and theta. Be sure that you take the positive square root. So the square root of R squared plus Z squared minus 2RZ is equal to R minus Z if R is greater than Z. It's very simple that the terms inside the square root is equal to R minus Z whole square. If you take square root, naturally you will get R minus Z. If R is greater than Z, but it is Z minus R if R is less than Z. For detailed discussion, you compare my problem in the example 2.8. In example 2.8, I have explained all this concept. So now you take this sphere and take small area element. Our aim is we have to find the electric field at a point Z outside as well as inside. First you take outside is Z, distance is Z, and you are taking a small area element uh, from which the distance of point under consideration is R. So the angle enclosed by Z and R is theta. So theta is an angle enclosed by Z and R. So according to cosine law, R squared is equal to this Z squared plus R squared minus 2ZR cos theta. So you differentiate this with respect to theta, that is T R over T theta. So this left hand side will become 2RTR. The right hand side, if you differentiate with respect to theta, first two term, there is no theta dependent. Third term, minus 2ZR cos theta. If you differentiate cos theta, you will get minus sin theta. So you will get 2ZR sin theta t theta. And now here, this 2 and this 2 will get cancelled. So you will get TR is equal to ZR sin theta T theta, and you bring this R to the other side. Here is R, you keep bring this to other side. So this will become already ZR is there, sin theta T theta over R. Then you bring this to the left hand side, ZR to the left hand side. This is some small mathematical trick. You can understand why I am doing this in due course. So TR over ZR is equal to sin theta T theta over R. So now you find the V of R potential first because it's a very simple way of approaching this problem. First find the potential. V of R is equal to 1 over 4 pi epsilon naught integral sigma TA over R. What is TA here? For spherical coordinate system, TA is equal to capital R squared sin theta t theta t pi. Now you have to integrate. You replace TA by this parameter. So you can take sigma outside because it's independent of R, and capital R square you can take. Now, if you integrate this t pi, t pi varies from 0 to 2 pi. So if you integrate it between the limit 0 to 2 pi, then you will get to 2 pi. So I brought that 2 pi outside. So sigma is there, and here r square I have taken out. And when you differentiate t pi, you will get 2 pi. And the remaining thing I am keeping as it is 4 pi epsilon naught integral between 0 to pi. Theta varies from 0 to pi. So sine theta, t theta over r. Here we know sine theta, t theta over r. We are going to replace this by this. We will let us see how it changes. So we got this expression. Now we can make some simplification. You cancel this 2 pi with this 4 pi, which will become 2. So naturally, you will get the sigma r squared in the numerator and 2 epsilon naught in the denominator. And I am going to replace sine theta t theta over r by this dr over zr, because we have already seen sine theta t theta over r is equal to dr zr. Now 1 over zr I am bringing it out because this does not depends on small r, and I am keeping this dr inside the integral, and I have to change this limit also. This limit is for theta, so 0 to pi. Now we have to change the limit. We have seen r squared from cosine law. R squared is equal to z squared plus capital R squared minus 2z capital R cos theta. Let us take the lower limit. If theta equal to 0, then what will happen? This cos 0 is 1. So this will become z squared plus r squared minus 2zr. This is nothing but r minus z whole square. So naturally r is equal to modulus r minus z. So the lower limit is modulus r minus z. What about the upper limit? Upper limit, here it is pi. If theta is pi, then this cos pi is equal to minus 1. So minus of minus will become plus. So r squared is equal to small r squared is equal to z squared plus r squared plus 2zr. So which can be written as r plus z whole square. So that means r is equal to r plus z because we are taking square root. Now you are, I have changed the lower limit and upper limit. So now we have to apply. If you integrate dr, we will get r, and of course you have to apply the upper limit as well as the lower limit. After applying this, before that we can cancel some of these. R squared will get cancelled with this r, which will become r. So outside the integral, you have sigma r in the numerator, then 2 epsilon naught z in the denominator. And of course, after applying the limit, upper limit is r plus z and minus lower limit is r minus z. Then we will try to simplify this further. Now we got this potential V of z is equal to sigma r over 2 epsilon naught z r plus z minus modulus r minus z. Now take the two cases. That is r is greater than z. That is inside the sphere. So potential inside is what will happen to the terms inside the bracket, because r is a bigger number. So this will become R minus Z. So this R will get cancelled in this case. So you have Z minus Z is plus Z. You will get 2Z. So naturally, this 2Z will get cancelled with this 2Z. So you will get sigma R over epsilon naught. If R is greater than Z, that is inside. Then what will happen if it is outside? If it is outside, if it is outside, you remove this. You can erase this. That is Z is greater than R, that is outside, it is outside, then what will happen here? Z is a bigger number. So this will become Z minus R because it's a positive. It's Z minus R. So in this case, what will happen? This Z and this Z will get cancelled. And you have R uh, minus R, that is minus R will become plus 2R. Now here this 2 and this 2 will get cancelled. You will get sigma R squared over epsilon naught Z. It is for outside. Then our aim is we have to find the electric field. The electric field by definition is a negative gradient of the potential. If you take dV by dz, here there is no z. Everything is constant. Sigma constant, capital R constant over epsilon R constant. So if you differentiate this, you will get 0. So inside the field is 0. One more thing is if you form a Gaussian surface, you have no charge inside the sphere because it's only charge is only on the surface. So this is a correct one. Then what about the electric field outside? Electric field outside, you have sigma R square over epsilon naught. You have to differentiate this. V is equal to negative gradient of gradient of the potential. Then if you differentiate 1 over z, you will get minus 1 over z square. So already here you have one minus. Minus of minus will become plus. So this will become sigma r squared over epsilon naught z square. Then we have to replace sigma. Q total charge is equal to surface charge multiplied by the area. That is 4 pi r squared sigma. Then what is sigma? You bring this to the other side. So sigma is equal to Q over 4 pi R capital R square. So if you replace the sigma by Q over 4 pi R square, this R squared and this R squared will get cancelled. You will get 4 pi in the denominator, only 4 pi, Q over 4 pi. So this will be Q over 4 pi epsilon naught Z square, which is exactly the result of what we have expected. That is, the uh, surface charge will act as a point charge, which is centered at the sphere, center of the sphere. If you find this lecture a helpful one, kindly subscribe. Also share my videos and join my channel in for the growth of my channel. Thank you very much for watching my video continuously and supporting me. Thank you very much.